Hello everyone, I'm Caleb with Wattage Wisdom, where we believe that anyone with the right motivation and internet access can become an expert in any field they desire. In this video, we'll be talking about how you can reduce the training time of your neural network. And if you've made it this far into your AI journey with us, I would ask that you please like, subscribe, and shoot us an email on how we can better serve you. So as I hinted at the end of our last video, along with accuracy, the biggest problem you will face as a designer is trying to reduce the time required to train your neural network. This may not have been a problem you've faced yet, as many simple applications have networks that can be trained in just a few minutes or even seconds. However, once you start to explore greater and more complex applications, you will need to rely on networks that require much more calculations, which result in a significant amount of training time. So while hardware can and does play a significant part in training time, this video will focus on software and coding tricks that you can use to reduce training time. So if you're trying to train a neural network on an old laptop of yours, please pay attention to the tips in this video, which can save you a boatload of time. When you want to go about reducing your network's training time, there are a lot of different ways you can go about trying to achieve this, and each technique is going to have its own level of difficulty and effectiveness. The first and maybe obvious approach is to reduce your model's size, specifically your number of layers and the size of each layer. As your model reduces in complexity, the amount of calculations it needs to complete also reduces, and thus the required training time decreases. However, when adjusting your model size, you must also take into account the memory required by your model so it can make accurate predictions. This is something we talked about in the previous video with overfitting and underfitting. Another thing you can do to reduce your training time is to make sure and normalize your input data before feeding it to your neural network. Normalizing your inputs helps stabilize the gradient descent and can help your model converge faster. This fairly easy step is explained in our first video outlining the neural network development process and is probably something you'll want to do regardless of if training time is a concern or not. We've also previously covered regularization methods like weight regularization, weight decay, and others which can help reduce the training time needed for your model to converge. So while the above techniques are rather intuitive, and all of these have been covered in previous videos, I will not dive into them any further. However, in the following slides, I will dive into methods like configuring your dataset, adjusting and tuning your learning rate, superconvergence, and utilizing transfer learning, which are all deeper techniques that can help you reduce training time. The first thing you can and should always do is properly configure your dataset. Configuring your dataset assures that your input-output does not become blocking and act as a bottleneck during the training process. Fortunately, TensorFlow provides us with two ways, .cache and .prefetch, which allow us to utilize buffered prefetching and speed up the training of our model. As seen in the example code, these functions are called after creating your training and validation datasets using the tf.keras.utils.image dataset from directory. The .cache method is used to keep the loaded images in memory after the first epoch. This assures that during your training, datasets will remain inside the memory and will not constantly need to be reloaded each epoch. However, this is with the assumption that your dataset is not too large. Otherwise, not all of it will be able to fit into memory. The other helpful function, .prefetch, allows the data processing to be overlapped with model execution while training the model. One useful optional parameter you can pass this method is the buffer size, which represents the maximum number of elements that will be buffered when prefetching. It is recommended that you pass this argument tf.data.autotune, as it allows the buffer to be dynamically tuned while training. These important steps of configuring your data can be used along with all of the other techniques described in this video and are essential to have in your toolkit, as they can help achieve peak training performance through building an effective input pipeline. The next thing I would like to touch on is the learning rate. I know we have previously touched on learning rate in the past few videos when talking about compiling your model and how it is an effective hyperparameter that can be tuned to find an ideal value. However, we will now further explore what the learning rate is and how it can affect the training and performance of our model. So, in general, learning rate is a hyperparameter that controls the amount or how much the model weights can change in response to the estimated error during the model update cycle. There are a wide variety of values you can choose from for this parameter. However, the one you go with should be carefully selected and tested, as it must be a balance between being too large or small. When we think back to our first video describing gradient descent, also known as finding the local minimum for the loss function, if our learning rate is too small, this will result in only a slight nudge down the slope and will require many update cycles and epochs before the minimum can be reached. On the other hand, if the learning rate is too large, the updates to the model will be too drastic, which can result in an unstable training process and divergent behaviors, where your model can actually skip the optimal set of weights. We must also take into account the learning rate in relation to our batch size, as there is a high correlation between these two parameters. Generally, when your learning rate is small, you want a small batch size to go along with it. And when you have a large learning rate, you want to make sure and pair it with a larger batch size. This is because a larger batch size gives you more data per update, which allows you to get a better estimate of your gradients so that you may make a larger leap in the right direction. For beginners, however, it is recommended to start your model off with a small learning rate and a small batch size. So, as you begin to progress in your machine learning skills and you start to experiment with more of these parameters, how do you find the correct learning rate? As we talked about before, you can perform hypertuning to find the ideal learning rate, or you can perform a learning rate range test, which we will look at in just a second. There are also modern techniques which have allowed us to be more adaptive with our learning rates. We will first look at the learning rate scheduler. This is a predefined framework that adjusts the learning rate between epochs as your training progresses. This graph lays out some of these popular learning rate schedulers and what happens to the learning rate as training progresses. The constant learning rate, without using a scheduler, is seen as the solid blue line, and starts at a low learning rate and retains this value throughout the duration of training. However, all the learning rate schedulers start at a much higher learning rate and then decay as training increases. This allows your model to make large changes in the beginning, and then as you approach the local minimum, the decayed learning rate allows your model to slowly fine-tune itself with the right weights so that it does not overshoot the optimal values. There are also quite a few optimizers out there that can adjust their learning rate during training. The Atom optimizer, one of the most commonly used optimizers, is capable of this, as it is able to adaptively adjust the learning rate of each parameter in the model, which results in a much faster and more accurate convergence. In general, when searching for an optimizer, I would recommend that you look at ones that can adjust their own learning rate, as this can make it much easier on your end, so you don't have to play around with trying to adjust this finicky parameter. Now that we've talked about learning rate schedulers and briefly touched on how to find a good learning rate, we can talk about the learning rate range test. This test is a popular method for discovering the largest learning rate values that can be used to train a model without divergence. This is important because if you are looking to reduce your training time, a larger learning rate can help you do so, and this test can help you find the maximum value. The learning rate range test works by linearly increasing the learning rate by a predefined amount at specified intervals. So essentially, it is a learning rate scheduler that is the inverse of the learning rate schedulers in the top right, as the learning rate is continually increased throughout training. After implementing this growing learning rate and training your model, you should plot the history of your training loss and observe a similar pattern to the graph in the bottom right. Initially, with a very small learning rate, your loss will essentially plateau. Then, as the learning rate increases, your loss will descend to some minimum value before it begins to explode and skyrocket upwards. This minimum in the training loss, marked here by the star, can lead you to your optimal learning rate, which is just slightly less than the value of the learning rate at this minimum or star. So, if one of your goals is to reduce training time and you want to perform this with a maximum learning rate, you can do the learning rate range test so that you know the maximum learning rate that can be applied to your model, either as a constant learning rate or as the starting value of a decaying learning rate scheduler. There are also other techniques of learning rate manipulation like superconvergence where you want to know the maximum learning rate that can be applied. We'll take a look at this on the next slide. Superconvergence is a relatively new discovery in the world of machine learning, and it involves training your network with a high cyclic learning rate that, when successfully employed, can result in receiving the same level of accuracy with only about a tenth of the training time, which severely reduces the time required to produce an accurate model. Overall, this is a pretty amazing feat. As seen in the plot here, the cyclic learning rate, ranging from 0.1 to 3 in orange, converges faster than the constant learning rate of 0.35 in blue. The cyclic learning rate also converges to a higher accuracy of 92.1% compared to 91.2%. So what exactly is superconvergence? Well, it essentially is a one-cycle learning rate that grows for half of the training process and decreases for the second half of training. This graph lays out the cyclic learning rate for a model to achieve superconvergence during training. As you can see, this process starts off with a very small learning rate, which then increases each training cycle until it reaches a maximum value about halfway through the training cycle. After that, the learning rate decreases at the same rate it increased until it reaches its initial learning rate. Overall, the theory behind this concept is that during the start of training, the model will begin mapping out the ideal direction to adjust the weights so it can minimize the cost function. Then, as the learning rate increases, the model will make larger steps towards this local minimum, which decreases the training time as the model is making large adjustments. And then for the last half of training, the model will decrease its learning rate so that it can fine-tune its values. The maximum learning rate reached about halfway through this training cycle, aka the tip of the triangle, is determined through the learning rate range test. And the minimum value, both the initial and final learning rate, is calculated to be around a factor of a 10th to a 25th of the maximum learning rate. Now, if you want to achieve an even more accurate model, you can add a small decaying tail at the end of your cyclic learning rate. This is seen at the bottom right of the graph at about the 8,000th iteration. This tail includes a very low learning rate, about 100 or 1,000 times smaller than the minimum learning rate, which is continually decaying and has the goal of fine-tuning your model to achieve the greatest total accuracy. It's best to train in this phase for around 5% or even less than 5% of your total training time, as you really don't want to begin overfitting your model. Now, there are a few other considerations when thinking about superconvergence. The first is that not all models are right for superconvergence. Only models that can handle large learning rates are optimal for superconvergence. This is something you must first test using the learning rate range test. Another thing to keep in mind is since superconvergence involves using a very large learning rate, you will want to have a larger batch size for training. In fact, the founder of superconvergence, Dr. Leslie Smith, states that you should use the largest batch size that can fit into your memory. And this is much different than traditional batch sizing approaches. Now, larger batch sizes also help reduce the time per iteration and speed up the training process. The last consideration is the effect that superconvergence has on regularization. Now, large learning rates oftentimes have an implicit regularization effect that they employ upon models during training. This means when using superconvergence with a high maximum learning rate, it reduces the need for other forms of regularizers like L2, weight regularization, and dropout. In fact, it has actually been observed that reducing other forms of regularization when using superconvergence actually increases the model's performance. So with this short summary of superconvergence, I highly recommend that you look into it on your own and begin testing it in your models, as it is honestly an extremely powerful tool that is not well known among the deep learning community, even though it can offer a variety of benefits and allow for an extremely reduced training time. A final way you can greatly reduce the training time required for your model is by utilizing transfer learning. Transfer learning involves using a pre-trained network to solve a new problem. This pre-trained network can be one you developed yourself, or it can be a model developed by someone else. There are tons of pre-trained models available online, and many of them are trained in a generalized way so that they can be fine-tuned to your specific application through transfer learning. For this example, we're staying in the world of image recognition, and so the pre-trained model we will have chosen is a convolutional neural network, which we'll cover in the next video. But basically, all you need to know is this pre-trained network will be used for feature extraction from our images. And it'll basically serve as our machine's portal into the visual world. And so, we will use the power of transfer learning to use an already trained network that only needs to be slightly adjusted with a few extra layers to complete our new classification task. So as I just stated, we're looking to use our pre-trained network primarily for feature extraction. This means we only want to include the first layers of the model that relate to turning an image into an encoded input, essentially right up to where you'd put the flatten layer. This is because all layers after that are related to classifying objects the network was previously trained on, which is not relevant to the new objects that we want to classify. This is something you declare when loading in your pre-trained model, where we have the optional parameter included top equals false, which means our loaded model will not include any of its classification layers. After loading this model, you will then want to freeze all layers in the model by calling .trainable equals false. This assures that all pre-trained weights in the model will remain unchanged during the training process, as you will only be training/updating your new classification layers. You can assure these layers are properly frozen by viewing a summary of your pre-trained model and seeing that it now has 0 trainable parameters. From here, we can now start to add our additional layers by chaining them together, starting with our inputs and ending with our output. However, we must be aware of the output size from our previously trained model. Note that the output from our pre-trained model is a 5x5 by 1280 feature block, seen here in the model summary. And so instead of using the flatten layer, as this would give us an output of 5 times 5 times 1280, we will use the global averaging pooling 2D layer, which applies average pooling on the spatial dimensions 5x5 until each spatial dimension is only 1x1, meaning we will end up with a 1x1 by 1280, or just a flattened output of 1280. This saves a large amount of data being flooded into our fully connected layers, which would drastically increase training time and is counterproductive to our goal of transfer learning. Now, after this global average pooling layer, we will continue to chain together our regularly fully connected layers and output layers, and then build, train, and use our image classifier like we've previously learned. So that is the basics of using transfer learning for feature extraction, but I would like to mention one other technique we can use with transfer learning known as fine-tuning. Now this involves unfreezing a few top layers so that they can be fine-tuned to map out features that are specific to our new classification images, as opposed to just extracting generalized features from an image. So this step is recommended if you want to produce a more accurate model, as the top layers of a convolutional neural network are usually set to map out more specialized features from an image, and so by fine-tuning these top pre-trained layers, you can greatly increase the overall accuracy of your model. Now, I'm not going to walk through this entire process again, as it's virtually the same process, except that when freezing our pre-trained model, we will leave a few layers at the top unfrozen. With this short introduction into transfer learning, I recommend you start searching the internet, try to find some pre-trained models of your own, and experiment with them. Alright, so that wraps up this video on ways you can reduce the training time for your artificial neural network. Definitely review this video as you start implementing these techniques in your own design process, and as you start trying to employ some of these concepts by playing around with the learning rate and using pre-trained models. Thank you all for tuning in. Please look out for my next video where I'll go into some more vision-specific applications like convolutional and Siamese neural networks and how they can be used to classify images and recognize objects. Of course, we're striving to put out more educational content each day, so remember to like and subscribe, and definitely shoot us an email with any questions, topic suggestions, or if you're looking to collaborate. I'll see you next time, and always remember that with the right motivation and internet access, you can become an expert in any field you desire.